All right, today, finally, we get to talk about the cause of all of this static electricity we've been talking about. And if some of you guys were dealing with the, if you guys were touching the sphere, the chrome sphere to the aluminum top on our Van de Graaff generator, you might have noticed that the rod would get pulled in right before you hear the spark. You get a right when it comes in. That's what's going on here. That you have an attractive force, and that force is governed by Coulombs law. Okay, and Coulombs law is the electrostatic version of the universal law of gravitation. You guys remember that one? Force of gravity equals universal gravitational constant times the mass of one object times the mass of another object divided by the distance between them. You guys remember this? Okay, and if we really want to get a little complicated, then it's negative r hat, which means it's that they're attractive, that if you have a massive object here and a massive object here, okay, and that's r, that the force is in the negative direction of that vector. So the distance from the middle of one to the middle of another, okay, and the force is actually pulling back in the other direction. Or if we, if you go the other direction, okay, and its force is back that way. So that's what the negative does. So if the r is in the direction of from one to the other, then the negative brings the force back. Well, we have a similar sort of thing with Coulomb's law, except this time, this is the electrical force, not the gravitational force. The electrical force given by K, and K has a value, K has a value of, we'll get there in a sec. It's a constant K, just like there's a constant G for gravity. Times the charge of one thing, times the charge on another thing, divided by the square of the distance between them. Oh my gosh, it's like the same equation, right? Instead of being mass, it's charge, and we just have a different constant, and we still have this r hat, which means it's just the directional. It just says it's in the direction of the radius. Now this k, so g over here was really, really small. It's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Okay, that's G. K is about 20 orders of magnitude larger. K equals 8.99 times 10 to the 9th. Okay, no, not negative 11th. Positive 9. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Remembering that a Coulomb is our unit of charge for our charges. Remember that an electron has a charge of 1.6 times 10 to the negative 19th coulombs. Okay, so we're dealing with, when we're charged particles, we're dealing with just a few exchanged electrons. Then we're dealing with a really small charge, but the force between them is still pretty large. Yeah? Okay. Right, so this is pretty much it, but you may be asking yourself, well, if this is a force, what do we know about charges? If you bring two charges together, what are they going to do? If you bring them close, they'll do one of two things. They'll either attract or repel, right? So there will be a force. There will be some force acting on the charges that will either bring them together or it will force them apart. Well, I want you guys to keep this negative up here in mind. That this mass, this negative meant that these two masses were attracted to each other. Okay, what happens if we... So we're going to look at this right here, this Q1, Q2 idea. Q1, Q2. Okay, if we're multiplying them, if Q is positive, and if Q1 is positive and Q2 is positive, what do you get when you multiply a positive times a positive? You get a positive. Okay. And what do we know about like charges? That if it's a positive and positive, are they going to attract or repel? They're going to repel, right? So if we get this product between them equals positive, then they're going to repel. What if Q1 is positive and Q2 is negative? Okay, positive times the negative is negative, right? And what do we know about opposite charges? They attract. So whenever you have, this is where it comes from, is that if you multiply these charges together, if you have a positive times a negative charge and you get a negative, this value becomes negative, and now all of a sudden it's attracted to, these two particles are attracted to each other. If we have negative times a positive, and that's going to give us a negative, which gives us an attraction, and then we have a negative times a negative. That leads to another positive, and that gives us a repel again. All right, so okay, like the like ones repel, and the opposites and the opposites attract. So that's where it comes from. It comes from Coulombs' law, and we assign the charges, and it works that if you multiply a positive times a negative charge, and they'll be attracted to each other. If you multiply, positives positives or negatives and negatives, then they'll wind up being a positive version, and they will push each other apart. So what does that look like? We get a if we get all these positives here, and we bring another positively charged thing to it, and that's the radius. Okay, this has Q1 and this is Q2. If they're both positive, then Q2 will experience a force that repels it from Q1. Yeah? And the same thing is that, so this is the force of 1 on 2. But according to Newton's third law, it doesn't just stop there. That the force of 1 on 2 is going to equal the force of Q2 on 1. Yeah? Okay, and then we can do the same thing the other direction. That if we have a whole bunch of negatives and positives, okay, we have this R, then it's going to experience a force positive times negative. So that would be a force in the opposite direction to the radius between them. And so this would be the force of, this is Q1, Q2. This would be the force of 2, 1, and this would be the force of 1, 1, 2, and they'd be attracting each other because they have opposite charges. Okay, but we also have this r squared down on the bottom, and they behave according to the inverse square law. So if you have two charges, Q1 if you have two charges and they're repelling each other with a force of 10 newtons, and then you increase the distance, okay, let's say these guys are 0.5 meters apart. Okay, if you increase the distance to 1 meter, what's the new force? And we'll say they are, they're repel. So they're the same charge. So how would we go about this? Okay, well, we know that FE equals 10 newtons. And R equals 0.5 meters, and the other stuff isn't going to change. So if what are we doubling? We're doubling our radius here, right? And so if we're going from over 0.5 meters squared, or we'll just call it R squared, and we change it to 2R squared, all of a sudden this is going to be okay, when we evaluate this, we get 2R quantity squared, which gives us a 4 in the bottom, which is 1/4 of what we started with. Yeah? Okay, so if we double the distance, our force decreases by a square of how much of how we increase the distance, right? So if we double the distance, then it's 1/4, or 1/2 squared is the distance between them. So so the force is proportional to Q1 and Q2, okay, and it's proportional to 1 over R squared. And that's pretty much it for Coulombs law. And we'll set you guys free to get going on your work.